Welcome at this practice exam number 1 for Calculus 2. This is a practice exam consisting of old exam questions, actual exam questions, and also a few questions that were not in exams but could have been. There are 4 open questions and 6 short answer questions in this exam, and we want to discuss them one by one here. Before you continue listening to this video, I want to warn you a little bit that listening to the questions that I discuss here might give the false impression that these questions are simple. I hope that I can make the answers and the workings understandable to you, but just be warned that understanding my explanation does not necessarily mean that you can make the questions yourself. So therefore, I advise everyone to first make this exam themselves before listening to this video, and never think that understanding my explanation means that you can do such a question on your own. That's a very different and difficult thing. Now, having said all that, let's go to the first question number 1. So in this question we are given 2 equations in 4 variables, and so I want to answer this question for you in 2 ways. The first way that I will present will make use of a standard formula that you can learn by heart and that was presented in class. And then the second way will be without using that standard formula, but just differentiating the equations and deriving the results step by step. Okay, so let me start. Before we take off in any of those 2 methods, I think we should first analyze the situation a little bit. So obviously there are 2 equations. I need to write that correctly. So 2 equations and 4 variables. It's important that we count these numbers, because if we have 2 equations, we know that we can describe the solution or the solution set of these 2 equations using 2 dependent variables and then the remaining variables will then in that case be independent. So this 4 minus 2 is also 2 independent variables. All right, so if we look at the question, we can find a clear hint as to what to choose for dependent and independent variables, because we see that we differentiate w with respect to x, which implies that w is dependent and x is independent. And then furthermore, we are to keep the variable y constant, and so that's also considered an independent variable. And it leaves us with only v, which then has to be also, just like w, a dependent variable. So that will help us. In our calculation quite a bit. All right. So also, what is I think very useful here is to name the equations. So maybe I should call the first equation f of v, w, x, and y, and then the second one, let's call that g of v, w, x, and y. All right. So let's start now with the first method of solving this. So we want to calculate the derivative dw dx while keeping y constant. And in class we learned that you can calculate such a derivative by means of Jacobians. So the standard formula, if you can memorize that one for this type of derivative involving 2 equations, obviously, is the following. So it's the Jacobian where we differentiate f and g with respect to x and v, and then divide that by the Jacobian dfg dwv. All right, so if we can calculate these Jacobians, take the quotient, then that should answer our question immediately, and that may be a quick way of solving this problem. So let me then go ahead and calculate both Jacobians. So let's start with dfg dxv. Right, that is by definition equal to fx gv minus fv gx. All right, so if we want to calculate those partial derivatives, then just take a look at the equations again. And if we differentiate f with respect to x, we see we get w plus y. And that has to be multiplied by the derivative of the second equation with respect to v, the partial derivative. So that's going to be 1. And now we subtract fv, which is the derivative of the first equation with respect to v. That's going to be w, and we multiply that by gx, which is also 1. And so we get w plus y minus w is just y. All right, so let's do the same thing for the second derivative. Not the second derivative, but the other derivative. So it's dfg dwv. Okay, so that's by definition fw times gv minus fvgw. All right, let's work that out. So fw is v plus x. Okay, that's a v plus x. gv is just 1. And then we subtract fv, which is w, right? And we multiply that by gw, which is also 1. So that will be together, if we combine that, v plus x minus w. And so now we can take the quotient of these two Jacobians. Don't forget the minus sign. And we find that our derivative, dw dx, while keeping y constant, is equal to minus y, so don't forget the minus sign, divided by v plus x minus w. All right, so that's the first method. And if you memorize this formula for this derivative, which only works if you have two equations, of course, then, you know, that's an easy way to get that answer quite straightforwardly. If you have more problems memorizing formulae like this, then you can also do it from first principles. So, which means that we're going to take derivatives of those two equations and then simply try to solve for the derivative that we are looking for. So let me show you how that works as well. Okay, so here's the second method. All right. And the second method is that we are going to differentiate both of these equations with respect to x, and then try to solve for the derivative dw dx while keeping y constant. Okay, so that keeping y constant is not doing much for us, except for the fact that now we know that y is a independent variable. And again, I should remind you of the fact that v and w are dependent variables. So for v, we have v is a function of x, and w is also a function of x. And y and x themselves are independent. Okay, so we have to keep that in mind if we're going to differentiate those two equations, because, you know, we'll see that we need chain rules and maybe product rules and things like that. So let me start with taking the derivative. So I'm taking a derivative with respect to x. All the terms are going to be differentiated. All right, so we start with the first equation. We have v times w. That's already a product of two functions of x, so we need the product rule. So that's going to be vxw plus vwx. And then the next term is also a product rule again, so it's going to be wx times x plus w. And then the third term will simply give us y, and then all of that has to be equal to 0. Okay, so the second equation gives us vx plus wx plus 1, and the derivative of y with respect to x, you know, 0, y is not dependent on x, so that's the second equation. All right, now we need to tidy up the first a little bit, because we see that this wx occurs twice here, so let me simplify that thing a little bit. So we have vx times w, and then combining the second and third terms, we get v plus x times wx, and then we have plus w plus y is equal to 0. Okay, so let's get rid of that first one. Okay, so now we have two equations, and there are basically two derivatives that we could calculate from this. That's the derivative of v with respect to x and the derivative of w with respect to x. Well, we're clearly interested in the derivative of w with respect to x. So the way I'm going to solve for wx is by, eliminating this derivative vx. And I can do that if I multiply the second equation by w. So let me immediately do that. So I multiply that second equation with w. So that's times w. This is times w, and then 1 times w. And now I've done that, I can subtract both equations so that exactly the first two terms will cancel out, right? And so if I do that, I subtract the second equation from the first, I get v plus x minus w all times wx, and we get w plus y minus w is equal to 0, so that's obviously also canceling out. All right, so that's now one equation, and there's only one derivative here, so now we can solve for wx, which is the thing that we're looking for, and we find wx is equal to, move the y over to the other side to get minus y, and then divide by v plus x minus w, and that's, of course, the same thing as that derivative that we were looking for. So that concludes our second method. So let me write up the answer in the answer box and leave it there. It's minus y over v plus x minus w. Done. So in this question 2, we are asked to find vectors v1 and v2 such that in those directions the function f that's given increases at 50% of its maximum rate. All right, so it seems that here we need to work with some directional derivatives. So let me remind you quickly of how that went. So the directional derivative in some direction u, where u is also always considered to be a unit vector, is equal to u dot the gradient of f. Just remember that. And also remember that in class we calculated this thing to be equal to the absolute value of u times the absolute value of the gradient times cosine of theta, where theta is, of course, the angle between both vectors, right? So if we have u there and the gradient of f here, then the angle between those is theta. And then if you want to calculate the maximal value of that directional derivative, the maximum rate of increase of the function f, then that occurs, of course, if the angle theta is 0, because in that case our cosine will be equal to 1, and so that's going to be the largest value that the derivative, the directional derivative, will get. And so we find that du of f, its maximum value, the maximal directional derivative, has to be equal to the absolute value of f at a certain point. So of course we get there by saying theta must be 0 then, and obviously u is a unit vector, so its length is 1. So now that we know how to calculate the maximum directional derivative, of course we can look at the question and see that we are asked to find the directions in which the increase of the function is 50% of this. In other words, if I look at the directional derivative in some direction v of f, then we're looking for vectors v such that the answer is exactly half of the maximum rate, like this. Okay, so find v, that's our goal. All right, so just having had that reminder, now we should actually start calculating some things. All right, so let's start by calculating that gradient at the given point. And then once we have found the gradient, we can see if we can solve for the vector v and find some answers there. Okay, so fx, let's start with this derivative. That's the first component of our gradient. And that fx is going to be, well, some chain rules, some product rules. You can check that it's y e to the power x times y sine of x plus y plus e to the power xy cosine x plus y. And then the derivative with respect to y is x times e to the power xy sine of x plus y plus e to the power xy cosine x plus y. So let's evaluate those partial derivatives at the point 0 comma pi over 2. So we find the partial derivative at 0 comma pi over 2 is equal to, all right, so just fill in pi over 2 there, 0 e to the power 0 is 1. We get sine of pi over 2, which is also 1. So this is 1, this is 1, that's pi over 2. So we get pi over 2 for the first term, and then the second one, e to the power 0 times the cosine of pi over 2, but that is 0. So the partial derivative with respect to x is just pi over 2. And then the partial derivative with respect to y at the same point is then equal to, well, okay, x is equal to 0, so that cancels the entire first term. And then again, we have cosine of 0 plus pi over 2, and so that's also going to be 0. Right, so there's our expression for the gradient at 0, comma pi over 2. It's equal to the vector pi over 2, comma 0. All right, and so now we want to enforce the following equation. So we're looking for vectors v, obviously, which have the property that we are at half the maximum rate. So, well, we use the definition of the directional derivative again. So df, or sorry, let me correct that. dv of f is equal to v dot the gradient of f, right? Which has to then be equal to a half times the absolute value of the gradient of f. All right, so let's work this out for the point 0, comma pi over 2. Well, let me start by writing out v in its components, and let's call those v1 and v2, not to be confused with the naming of those vectors. So v1 and v2 are the components of some vector v here, right? So the dot product with pi over 2, comma 0, that's that, which has to be equal to a half times the absolute value of the gradient. But we see that if the gradient is pi over 2, comma 0, the absolute value is just pi over 2. So this has to be pi over 4. All right. So now let's work out that dot product. So that's going to be v1 times pi over 2 plus v2 times 0, and that has to be equal to pi over 2, from which we conclude that v1 has to be half, right? And that also gives us v2, because, you know, v by definition must be a unit vector, and so a unit vector tells us that v1 squared plus v2 squared equals 1, and if v1 is a half, then v2 has to be plus or minus a half square root of 3. Right, both are correct, both give us unit vectors, and both will give us the same dot product. So these are the vectors that we're looking for. So v1 is the vector a half minus a half square root of 3, and then v2 vector is equal to a half, comma, plus a half square root of 3. All right. So that concludes this question, and the answer here are those two vectors. So that brings us to question number 3, which asks us to reverse the order of integration for this double integral. And this double integral is an integral over a y-simple region, which we can see because we're starting to integrate over y, and the boundaries for y are functions of x. And so if we want to reverse the order of integration and start integrating over x, then we need to describe the integration region somehow as a x-simple region. So to that end, what we want to do is we want to visualize the region and see if we can come up with a good x-simple description of that. So let me do that. Okay, so let's see. Y is bounded between 3 and that square root of 25 minus x squared. So let me start with the 3. That's a horizontal line at y is equal to 3. And then the square root of 25 minus x squared, what is that? Now let us take a look at that. So if y is equal to the square root of 25 minus x squared, then y squared is equal to 25 minus x squared. So that x squared plus y squared is 25, which is 5 squared. That's an equation of a circle, and that square root gives us the upper half of that circle of radius 5. All right, so we can draw that as well. Let me draw that. Okay, so the intersections with the x-axis here are 5 and minus 5. All right, and so we also can notice that those two curves, they intersect here, and you can easily show that this intersection will be at minus 4, and this intersection will be at x is equal to 4. All right, so let's now take a look at the boundaries for x. Well, the lowest values of x that are in this region are exactly at this minus 4. So this intersection that we already found is our lower bound. And then when x is equal to 0, that's the largest values of x that occur. Okay, so our region is now constricted to this little segment over here. All right, so now we want to describe this thing as an x-simple region. And that means that, of course, we want to integrate it over x. And if we do so, our lower bounds for integration will always be given, of course, by this segment of the circle, the circular arc over here. All right. So let's find the x values for that circular arc. Well, we know that x squared plus y squared is 25. So we find that x has to be equal to plus or minus the square root of 25 minus y squared. But obviously, that circular arc is located on the negative side of the y-axis. So it's going to be, the lower bound is going to be minus the square root of 25 minus y squared. So that's a lower bound for our x integration. And then obviously the upper bound is going to be here where x is equal to 0. All right, so that gives us a bounds for the x integration. Then if we integrate out over x, we are left with an integral over y, which will then be over all the possible y values in our little region. And so that is going to be bound between 3 and 5 here, right? So the boundaries for y are 3 and 5. So we can express our final integral as the following integral. So for x, it's minus the square root of 25 minus y squared all the way to 0. And so that's integrating f over x. And then for our outer integral over y, we integrate from 3 to 5. All right, so that will conclude our question, and this is the answer. And that brings us to question number 4. And so in question 4, we consider a fishbowl with a shape that's defined as the bottom part of a sphere of radius 3. And of course, that region is given as a set of points in the three-dimensional space as shown here. And the first part of the question is to express the volume of that region as a triple integral in cylindrical coordinates. So we have to somehow calculate the volume of B. So let me call that V of B. And, you know, one thing that we really have to understand is that the volume of such a region is just a triple integral of the function 1. So somehow we need to evaluate this integral for both parts of this question. And in the first part, more particularly, we have to set up that integral as an integral over cylindrical coordinates. Now, we don't need to actually calculate that integral, right? That's an important thing. The main objective here is to express the integral and its boundaries. All right, so, you know, I think it's always a good practice to sketch that region first. So let me just sketch that region. And we have to understand that this is the shape of a sphere, which is not centered about the origin, but it's basically a sphere of radius 2 shifted downward by 2 units. All right, so the center of the sphere is at z is equal to minus 2, as we can see from that description. And then it's also cut off. So if we look at this description, so it's centered at minus 2, as we can see there, but it's cut off from the top, right? And so that surface looks a little bit, or that not a surface, but that volume looks a little bit like this. So the cut off part will be some circular thing here, and then it's just a cut off sphere like this. And so it's a sphere of radius 3, as we can see from the 9 there in that equation. And so the bottom part will be minus 2, minus 3 will be minus 5. All right, so, okay, well, that's actually going to be helpful here. Now, if you want to express this as an integral over cylindrical coordinates, then just let's start with that description. So what we see here is that x squared plus y squared plus z plus 2 squared has to be less than 9. Which means that in cylindrical coordinates we get r squared here. So r squared plus z plus 2 squared is less than 9. And then we can work that out for r and see what that implies for r as a function of z. So, of course, r squared has to be less than the square root of, or not the square root, sorry, of, has to be less or equal to 9 minus z plus 2 squared. And that only happens when r is between two values. It's between the positive square root of 9 minus z plus 2 squared and the negative square root of 9 minus z plus 2 squared. Right, but then, you know, that lower boundary is really not what we need, because we already know that by definition of the cylindrical coordinates, r always is larger than 0. So the upper bound is good, but the lower bound for r is not this negative square root. It has to be equal to 0. So we find that r is between two values. It's greater than 0, but less than 9 minus z plus 2 all squared. Now that's actually most of the work. If we look at the figure, we see that, you know, all values of theta are included in this fishbowl shape. So theta will go between 0 and 2 pi, and then z will be between its minimal and maximal value. Well, the maximal value was 0 and the minimal value was minus 5, as was already given in the description of B. All right, so that will give us an integral. Well, so let's start with the inner integral over r. R is bounded between 0 and the square root of 9 minus z plus 2 all squared, right? And then we have an integral over theta, which is between 0 and 2 pi, and then we have an integral over z between 0 and minus 5. Then we have to think about the integrand, of course, because we integrated the function 1 over the volume. But then, of course, in cylindrical coordinates, you have to remember that it's not just dr, d theta, dz, but there's that Jacobian, which is equal to r. So there's going to be an extra factor of r here. And so the integral will eventually become this. And that concludes the first part of this question. There's the cylindrical integral. And for the second part of this question, we're going to do exactly the same thing, but we're going to express our integral in spherical coordinates. So let me just, as a quick reminder, picture that region. We hopefully have it in our minds already, but there we go. So x, y, z axis, and here's our fishbowl, the upper part, and then the sphere, where the lower part is at minus 5, the center of the sphere is at minus 2, and the upper part is in the xy plane at z is equal to 0. So now, in order to work out the integral bounds in spherical coordinates, I want to start again with the description for B. So let's start with that sphere. X squared plus y squared plus z plus 2 squared is less or equal to 9. And it might be a good idea to start writing this in terms of capital R, which is the distance to the origin in spherical coordinates. So let's just first work out the square here. So we get x squared plus y squared plus z squared plus 2 times z plus 4 is less or equal to 9. All right, and now we notice that this part here will simply be our spherical r squared, and that our 2z is going to be 2 times r cosine of phi, which is the angle with respect to the positive z-axis. And then the other parts can be combined into minus 5 is less or equal to 0. Now I want you to notice that what we have here is a quadratic inequality. And so we can find bounds for r by looking at the equality and just noticing that, you know, that this is a parabola. This shows you some parabola for any value of phi. That's looking somewhat like this. And that the entire thing is negative, less or equal to 0, between these values of r. So this is your minimum R, and this is your maximum R. Okay, and this is of course all R values right here. Now, if we want to solve this inequality, of course, we first need to find the zeros of this equation. So let's do that by applying the ABC formula. So the ABC formula gives us the following. It tells me that minus b is minus 2 times cosine of phi plus or minus the square root of the discriminant. And that's b squared, which is 4 times cosine squared phi minus 4 times 1 times minus 5. That's actually going to be plus 20. And then we divide that thing by 2 times a, and that's 2. Okay, and we can simplify, we can divide out by 2 to find, well, by the way, these are the R values of those roots here. And then we can find that R is actually minus cosine of phi plus or minus, well, transfer that a half in the square root, we get cosine squared phi plus 5 here. All right, now that will give us an upper bound and a lower bound. And so as I can see in this picture here of the parabola, the upper bound will be where the plus sign is. So we can find that R has an upper bound of minus cosine phi plus the square root of cosine squared phi plus 5. And a lower bound of minus cosine phi minus that square root. All right, but if you think about that, the lower bound for R is clearly a negative number, and it shouldn't be negative because R is by definition positive, and we have also seen that with the cylindrical coordinates. So this is not a good lower bound for R. In fact, a good lower bound in this case has to be 0. Right, so it's a stricter lower bound. And the upper bound here, well, you can take a quick look. That is that this square root is of course greater than the square root of cosine squared. So this entire square root is greater than cosine of phi. And so that will be positive. And so this thing here is going to be a good upper bound. So cosine phi plus the square root of cosine squared phi plus 5. It's a complicated upper bound, but it's a correct upper bound. All right, so now that we have an upper bound and a lower bound for R, just take a look at the other variables. Let's start with phi. And for phi, I want to take a quick look at the picture that we have here. Because, you know, phi is the angle. If this is a point, then this is the angle phi. It's the angle with respect to the positive z-axis. But you see that this entire fishbowl shape is below the xy plane. And so the largest or the smallest value of phi that we have in this plane is actually when phi is equal to pi over 2. So, right, so this is exactly a 90 degrees angles here, so pi over 2. But then in that shape, you know, phi increases towards its maximum value of pi. And that's exactly the point where we are here on the z-axis. So we can find some easy bounds for phi. It's always bigger than pi over 2 and less than pi. All right, and then again, we are left with the theta bounds, but again, this theta is the same theta that we saw before with the cylindrical coordinates. That thing is a spherical symmetric object, and all values of theta between 0 and 2 pi are included. So we have 0 and 2 pi as bounds. So now we can start building our integral. Let's start with the first integral over R. It's going to be from 0 to that long expression minus cosine phi plus the square root of cosine squared phi plus 5. All right. And then we have the integral over phi, which goes from pi over 2 to pi. And then we have the integral over theta between 0 and 2 pi. Okay, so those are the bounds. Then as for the integrand, we were calculating the volume, so we're integrating the function 1. But again, of course, we have the Jacobian, and you have to memorize that Jacobian to be r squared times sine phi like this. And now we can integrate over r, then over phi, then over theta. And this is our final answer in terms of spherical coordinates. There we go. Now, in question 5, we are asked to calculate the area of a region in the xy plane that's enclosed by the given curve. And the hint here is to use Green's theorem. Well, okay, so before I'll take a look into Green's theorem, I think it's always a good idea to find some sort of a sketch of the region. And so, of course, we have the parametrization RT, which is a cosine of t, comma 2 sine t, cosine t, where t is bounded between the values minus pi over 2 and pi over 2. Okay, so let's first try to sketch that. It's not necessary to do so, but I think it's nice to, to have an idea of what we're doing in this calculation. So here's the region in the xy plane. Well, if we start at pi over 2 or minus pi over 2, we have to conclude that cosine t is 0 there. And so both components of this vector will be 0. So we are going to start at the origin here. And then for the endpoint, we have the same thing. If t is pi over 2, then we are at the point 0, 0. So it seems indeed that this curve is somehow closing on itself. Now, what happens if you start at minus pi over 2 and you increase the value of t? Well, you know from a cosine, what does a cosine look like? It looks like this, right? So this is a cosine. If we are here, then that cosine of t is going to increase. So the x value is going to increase. We're moving to the right in this picture. And then the same thing actually happens for the y coordinate. So cosine will increase, and also the sine. What is happening to the sine? Well, it will also increase from a negative value, right? Because the sine will look like this. It will be negative here, and it will also increase. So we get this kind of curve, and then it will loop back into itself like this. All right, it's just a little sketch. The region enclosed here is the region D, and I will call this curve C. Okay. Not really necessary to visualize this, but we want to sort of feel what we are doing here. That's actually a good idea. So let's just recap on Green's theorem. So Green's theorem says that if I integrate over a region D, the following thing, dq dx minus dp dy, where q and p are just functions of x and y, then that integral, that double integral, will actually be equal to the integral over the boundary C of p dx plus q dy. Okay, now that's a very general thing. You might remember that this theorem can be used to calculate areas. In fact, you should remember that, because that's exactly what we want to do in this question. And the trick here is to choose the q and p functions to be such that those derivatives on the left-hand side will be equal to 1. So the q dx minus the p dy is equal to 1. And if that is the case, then it turns out that we're calculating the area of the region D here. So if you integrate 1 over some region, then you're calculating the area of the region. And so that can now be calculated as an integral over the boundary. So p dx plus q dy. All right, so that's something that we might want to use. Okay, so now we have to choose p and q such that those derivatives add up to 1. And there are many ways to do that. So let me just choose p and q such that this works. But, this is just one possible choice, and you can do many more. I will choose p equal to minus y and q equal to 0. And that will simplify everything. You can, verify that the derivatives will add up to 1. And then the area of the will then be equal to the integral over C over the boundary of p dx, and q dy will then be 0. So if we take this and we know that p is equal to minus y, we get minus the integral over C of y dx. All right. So we want to calculate that integral. Oh, let me put the equal sign there. We want to calculate that integral, and just realize that we're taking the integral over the path defined by this vector function. So we see that the x component is cosine t and the y component is 2 times sine times cosine. So let's just use that here in our integration. So x is cosine of t, and y is 2 times sine t cosine t. Okay, and of course I want to have a look at this thing here. So if I want to I want to use these functions here for x and y, then of course I have to find the differential dx, which is given by minus sine t dt. All right, now, so let me just put that all together. So the area of our region D is going to be minus the integral over c of y dx, which is minus the integral of y, and that's 2 times sine t cosine t, times minus sine dt. So that's going to be minus sine dt, gives me an extra sign, so that will be sine squared, and that minus will make this minus plus, and then we integrate it over t, where t runs from minus pi over 2 to pi over 2. So that's the integral that we want to calculate. Now, how do we deal with that? Well, let's just use this u substitution here. So we can use u is equal to sine of t here. That will be very convenient. So let's see how that works out. Du will then be, well, the derivative of sine, which is cosine t dt, and well, the boundaries, if t is equal to minus pi over 2, then u is equal to minus 1. And if t is equal to pi over 2, then u is equal to 1. So we can rewrite the entire integral as this, the integral from minus 1 to 1, 2 times u squared du. Right, that looks like a fairly straightforward integral. Now let's work this out. This is going to be a 2/3 u cubed, and then we have to evaluate that between 1 and minus 1, and we see that that will be 2/3 plus 2/3 is 4/3, and that's the final answer to this question. There we go. That brings us to question number 6, and in this question we need to calculate the flux of the given vector field through a surface defined by z is equal to x squared plus y squared. And not just anywhere, we take the part of that surface that lies directly above some triangular region R. All right, and then we don't need to actually calculate the flux, but we want to, we want to set up an integral that calculates the flux, and if we can do that, then it's the end of the question. So let us just think this through a little bit. So what we want is the flux, and so we need to evaluate the double integral over the surface. Let me call the surface S here, of the vector field, right, over the oriented surface. So now apparently we need to rewrite this flux integral as a double integral over y and x. So somehow we need to rewrite this in this form, where the integral looks like this, right? So we have L2, U2, L1, oops, not T, L, get rid of that T, L1 and U1. Okay, how are we going to do that? Now, to this end, it makes a lot of sense to take that surface and parameterize it, and not just take any parameters, but take x and y as parameters. And it seems that the description of the surface, z is equal to x squared plus y squared, lends itself very well to that. So, of course, a parameterization for this surface would be r of x and y, where the x component is x, the y component is y, and the z component is then x squared plus y squared. And so now that we have that parameterization, we can immediately think about what that oriented surface element actually is. And just remember that this is equal to the normal vector of that thing times the area element. And in our case, we of course parameterized as functions of x and y. The area element is simply going to be dx dy. So this is the normal vector at each point times dy dx, where I'm sticking to the order that we have to solve this integral in. Now we have learned that we can calculate normal vectors by taking the cross products of the partial derivatives of these parametrizations. In other words, the normal vector that we're looking for is either plus or minus the cross product of r differentiated with respect to x times r differentiated with respect to y. Okay, so, and it's plus or minus depending on what eventually in what direction the normal vector is pointing. Now, we're looking, according to the question, for an upward flux. So we want to choose our n. We want to choose, in the end, we want to choose n such that it's pointing upward. So pointing upward. So upward means in the direction of increasing z. All right, so let's try to calculate that thing. Rx is the partial derivative with respect to x is going to be 1, 0, 2x. And the partial derivative with respect to y is going to be 0, 1, 2y. And if we work out that cross product, we will obtain the following vector, minus 2x, minus 2y, 1. And just notice that this vector is already upward pointing, so we can, so we can ignore the plus minus. We have chosen the plus one here, which gives us this normal vector. This is exactly the one that we are looking for. So now that we have that area element in place, we can actually start calculating the integrand of that flux integral. So f ds is f dot n dy dx. And so, since we know that f is the vector field z, 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 all components are z, we take the dot product of that with our normal vector 2x, minus 2y, 1, and integrate that thing over dy and dx eventually. Now, of course, we're not integrating just anywhere. We're integrating on the surface that is given, right? So it's an integral over the given surface, for which we know that z is equal to x squared plus y squared. And so we're going to use that to rewrite this one step further. So it's going to be x squared plus y squared, x squared plus y squared, x squared plus y squared, dot minus 2x minus 2y, 1 dy dx. And so that will give us x squared plus y squared times minus 2x minus 2y plus 1. And that's actually already our integrand of our flux integral. So that's solving almost the entire question. There's only one thing that we need to figure out, right? So this is f of x and y, dy dx, f of x and y times dy dx. The only thing that we still need to figure out are the bounds of integration, right? What are the upper bounds for y here, and what are the upper bounds and lower bounds for x? Okay. So to that end, we have to look at that triangular region, because we're not just looking at the entire surface, we're looking at that surface that is equal to x squared plus y squared, just right above that triangular region with the given vertices. So let me just draw that, and let me then try to describe that region as a z-simple region, because in the end that's how we want to calculate the integral, first over y, then over x. So we are given the coordinate here, 0, 1, 0, the coordinate here, 1, 0, 0, and then the coordinate here, which is 1, 1, 0. And the triangle will look like this. So we describe this as a z-simple region, meaning we're going to integrate over, sorry, not z-simple, but y-simple. We integrate over y first, and then over x. So this is the direction of integration. Now we're starting on the diagonal line here, and you can easily find that that's y is equal to 1 minus x. And then we integrate all the way until y is equal to 1. Right, so let me just write up the entire final integral now. All right, so the first integral is from y is equal to 1 minus x to y is equal to 1. The integrand is the thing that we have found above, so x squared plus y squared times minus 2x minus 2y plus 1. First integrated over y, finally integrated over x, and the values of x are, of course, between 0 and 1, all values of x that occur in this region. So we end up with the final result here, our flux integral. So here we come at the open questions of this practice exam, and question 7 is a line integral that we can evaluate. So there are basically three ways that we can calculate line integrals. First of all, if our curve C is a closed curve, then we can apply Green's theorem. So that's one possibility. If that's not the case, then we can either just calculate that line integral by parametrizing the curve and just work out the details of that integral. So straightforward integration. Okay, and then, well, but if we are lucky, then the vector field that we are integrating here is conservative, and in that case we can apply the fundamental theorem for line integrals. So let's check this. Now, in order to rule out some options, let's check whether the curve is a closed curve, and we can do that by checking the starting point and the end point of the curve. So the starting point of the curve is at r for t is equal to 0, and we can see that both x and y will be 0 there. So the starting point is at the origin. And the end point, when t is equal to 1, we can check that. So the x component is going to be minus pi over 2 times 1 times e to the power 0. That's also 1, so it's minus pi over 2. And the y component is going to be 2 times 1 times the sine of pi over 2, which is 1, so that's 2. So that's nice, because now we see that this curve is not a closed curve. The start point and the end point are not coinciding. So we can rule out Green's theorem, because that only works for closed curves. All right, so in order to see whether we can apply the fundamental theorem or we should straightforwardly integrate, what we have to check is whether our vector field is conservative. So and we can do that by trying to find a potential for this function. So let me start by giving the vector field. So the x component is 9x squared y plus cosine of 2x, and the y component is 3x cubed minus 8 e to the power y. Okay, so now if this vector field is conservative, then the x component is going to be the partial derivative of the potential with respect to x, and the y component is going to be the partial derivative of that potential with respect to y. And so we can try to find a potential by integrating one of these things, one of these components, and then see if we can find something that works. Right, so let me do that here, and let's start with the x component. So we can see that if there exists a potential, then that potential should be obtainable by integrating the partial derivative of phi with respect to x over x. And so we can try to do that. And if we look at the terms, then 9x squared y will give us 3x cubed times y, and then cosine 2x, that will give us a half sine of 2x. And then there's, of course, an integration constant. But since we're integrating over x, the integration constant may still be a function of y. So far, so good. And now we need to check whether this potential also works with for the y component of the vector field. So the y component, 3x cubed minus 8 e to the power y, should be the partial derivative of the potential with respect to y. Now we can check whether that works with our expression here. So let's differentiate that thing. Here's still a question mark. Well, if we differentiate it with respect to y, I get 3x cubed plus 0 from the sine of 2x plus the derivative of c with respect to y. And we see that that works very nicely for this term. And it also seems to work for the other term. If I find a c, that gives me minus 8 e to the power y. So dc dy is equal to minus 8 e to the power y. Well, that implies that c, the constant that depended on y, is also minus 8 e to the power y plus maybe some other constant. Let me call that c1. So it seems to work, and let's put everything together now. So we find the potential, because this is, we found no inconsistencies here. 3x cubed times y plus a half sine 2x plus minus, let's make that minus 8 e to the power y plus some arbitrary constant c1. Well, that's a good potential for our vector field. And so it means, if we go back here, that we can actually apply the fundamental theorem for line integrals, and that's very convenient, because now it comes really down to evaluating only our potential at the initial and end points. So let me do that. Let me just quickly remind you of that fundamental theorem for line integrals. So it says that the integral over a curve C of a vector field, if that vector field is potential or has a potential, then it is of this form, which can then be, which is then equal to phi evaluated at the endpoint of the curve. Well, let's check what's the endpoint. It's minus pi over 2 comma pi 2 minus pi over 2 comma 2 minus phi evaluated at the starting point, and that was 0 comma 0. So let's evaluate this thing, phi at minus pi over 2 comma 2. What's that? That is 3 times minus pi over 2 cubed times 2 plus a half sine 2 times minus pi over 2, that's minus pi, minus 8 times e to the power 2. And then we can, of course, ignore the integration constant here. And then we have to subtract phi at 0. So it's minus, and the first term will give me 0 there. The sign will also be 0. And then we have to subtract minus 8 e to the power 0. That's minus 8 is plus 8. All right, so let's evaluate this. Let's just write this up a little neater. So it's 3 minus 3 times pi cubed over 8 times 2, so that's over 4. And then plus a half sine minus pi, but that's 0. And then minus 8e squared, and finally plus 8. And that's our final answer to this problem. So question 8 is a question about the Navier-Stokes equation. And we are asked to rewrite the first equation here by first taking the curl of the entire equation and then simplifying each term to arrive at the second equation, which is a simple equation for the derivative of the vorticity. Now, we may use here the definition of vorticity, which is the curl of the velocity field. And we may also use a list of differential or vector differential identities. That's this list here. You may find this list, of course, on your own exam or your practice exam. So I'm not going to show it here during my calculation, but instead I will refer to each equation when I'm using it. So I'm now going to remove that list of equations and start calculating. So all right, let's start by taking the curl of the first equation. So it's the curl of the derivative of the velocity field with respect to t. That's equal to the curl, or let me say minus the curl, of v dot nabla acting on v minus the curl of the gradient of p divided by rho minus the curl of nabla phi, big phi. Okay, so we want to rewrite this, and let me do that by starting with the first term, then go to the second term, and just do this term by term. Okay, so here's the first term, the second term, the third term, and here's the fourth term. All right, so the first term, 1, we have the curl of the time derivative of the velocity field. But here we can interchange the order of the differentiation. So we can take the time derivative of the curl of v. But the curl of v is omega, that's our vorticity. So this is the time derivative of vorticity. And that's very nice because that's also the first term in our required equation. Okay, so let's go to the second term. let me for a small moment ignore the minus sign for simplicity. Well, we see that we need to take the curl of a very complicated vector, which is this operator acting on v. So I think it's a good idea to first start rewriting this thing and then take the curl of that. So let me do that. V dot nabla times the vector v. So now in order to rewrite this, we really want to take our list of formulae and find something there that is exactly of this form, like a vector dot product with an operator times another vector. And you'll find that you'll find that kind of term in the equation f. So I'm going to reference that equation here by saying this is equation f. And by the way, if you are using formulae in your exam, formulae that I give you on a sheet, please do that. Just reference the formula that you're using, because otherwise it's going to be really hard to follow what you're doing. All right, so let's look at f. Well, the formula f tells me that the gradient of the velocity dotted with the velocity is equal to 2 times the vector v cross product the curl of v, which of course is again omega, and then plus 2 times v dot nabla acting on v. Now that last term is obviously what we want to describe there. And by the way, in the formula f in your list is not about two of the same vectors, v and v. It's of course there the vector f and g, but you can take f and g both to be equal to v, and then you get this expression. So I find an expression for v dot nabla v by just rearranging the terms a little bit, and I'll get a half times the gradient of v dot v minus v cross product over the curl of v. Okay, so that's that. And so now that we have that expression, it still doesn't seem that we have simplified quite a lot, but of course we still need to take the curl of that thing. So let me do that right now. So now the curl of that thing is going to be, well, it's going to be the curl of a gradient as a first term. So if I take the curl of a gradient, we know that that thing, that the value of that thing is always going to be equal to 0. And I know that because of the identity that is given in the formula K. All right, it's also something that we discussed in class in some length. Okay, so that first thing is going to cancel out. It's going to drop from our equation, so that simplifies quite a lot. And then still we have minus the curl of v cross the curl of v. But the curl of v is omega, so this is the curl of v cross omega. And so that's a very nice expression, actually. So let me get back to the initial term in our equation that was minus the curl of this complicated expression, and that's now going to be equal to plus the curl of v cross omega. All right, up to the third term. Well, the third term is going to be minus the curl of nabla p over rho. And of course, you know, it's not just nabla p. If it was just a gradient, then this would be 0. But unfortunately, we're dividing by a function that may depend on a position. And therefore, of course, this term is not entirely 0. In fact, we can find an expression for it if we go to equation number C, because I can consider this a vector field times a scalar function, and the scalar function is 1 over rho. So if I do that, then equation C will give me that this has to be equal to minus the gradient of 1 over rho cross product with nabla p, the gradient of p, minus 1 over rho, the curl of the gradient of p. But then, of course, that's again a curl of a gradient. And so equation K tells me that that expression will be 0 again. So we end up with minus the gradient of 1 over rho cross the gradient of p. Now this part is still not in the required form because, you know, the equation that we're looking for has, like you can see here, has this form. So we still need to do some rewriting. And we can do that by thinking about that gradient of 1 over rho a little bit further. So let me calculate that gradient term by term. So the first term would be the derivative with respect to x minus the derivative with respect to x of 1 over rho. Then the second term would be minus the derivative with respect to y over 1 over rho. And then we end with the third component. Oops, let me go back. The dz 1 over rho. All right, so what is this? Well, how do you calculate those derivatives? Well, I think that here the chain rule would really help. So if we start by taking a derivative of 1 over rho with respect to rho, we got minus 1 over rho squared together with the minus sign that's already there. It's 1 over rho squared. And then, of course, we multiply that by the partial derivative of rho with respect to x. And then for the other derivatives, you get similar terms, obviously. So 1 over rho squared d rho dz, and if we combine that into a vector, then we get that minus the gradient of 1 over rho is actually equal to the gradient of rho over rho squared. And so that is that's an expression that we can use here. So in the end we get minus the curl of nabla p over rho is going to be equal to the gradient of rho over rho squared, and then we take the cross product with nabla p, so it's going to be the cross product of the gradient of rho with the gradient of p divided by rho squared. Now we're almost there, but in the final expression here in blue, we can see, of course, that we have nabla p cross nabla rho in the opposite order, and we can get that at the cost of a minus sign. So this is just minus nabla p cross nabla rho over rho squared. So that works out very nicely. Okay, that brings us to our final term. So 4 is minus the curl of nabla phi. That's a gradient, a curl of a gradient, and we have seen already a couple of times now that equation k tells us that that should be equal to 0. So that's our final term. That will simply vanish from our equation. And now we can see that if we combine each of those results, this one, and let's see, what did we have? This one and this one, that we really get the first equation. And so that answers this question. And that brings us to question number 9. Now in this question we are given a vector field of a particular form. It is a vector field that is that has a direction that's proportional to the vector, a direction of the vector v, but a proportionality constant, which is some function depending on position in space f. And for this particular vector field, we are going to derive an integral equation that is asked in the third part of the question. And as a preparation, we have to go through 2 steps. Well, the first step is to show that the divergence of this vector field is actually equal to v, the vector v dot the gradient of f. And in the second part, we need to show a unit normal vector of a spherical surface. So let us start with part A. Okay, A. Well, we know that the vector field f is equal to some function times the constant vector v. And so we can simply take a divergence of f, which is then the divergence of fv. And then in our list of vector differential identities, we see that we can calculate this divergence using the rule number b. Number b, it's more like a letter. But let's apply that rule so that we find that nabla dot f eventually is equal to the gradient of f dot v plus f, the divergence of v. But then, you know, we're taking here a derivative. The divergence of v is a derivative of v, and it is already given that v is a constant. So this is equal to 0. And then, well, this is actually already our correct answer, but we can, of course, shuffle the two vectors to see that this is equal to v dot the gradient of f. So that definitely answers part A. So we go to part B. And in part B, we should find a unit normal vector of the spherical surface S. Okay. Now, there are a couple of approaches here. And, well, first, you know, we have seen this normal vector in class. And here the question is to really show that it's x, y, z. So you cannot simply say, well, we have learned in class this and this and that. Now we have to really show how you get that normal vector. That's one. But then there are different approaches that we can use. And I will use one approach here that is really convenient and fast. And that is to consider our spherical surface as the level surface of some function of 3 variables. I will quickly also, after that, I will quickly hint at some other approaches that may work, but are probably taking a little bit more time. So let me do this the quickest way I can think of. So let's say the unit sphere, which is the surface S. The unit sphere is a level surface of the function f of x, y, and z, which is equal to x squared plus y squared plus z squared. Okay, because x squared plus y squared plus z squared is equal to 1 is just where f of x, y, z is equal to 1, so that by definition is a level surface. And so that's a very useful given, because I know also, we have seen in class also that the gradients of these functions are actually perpendicular to the level surfaces. So we have to use now that the gradient of f is actually perpendicular to the level surface. And that means that if I simply take a gradient of this function, we already have a normal vector. And then we have to only make sure 2 more things, of course. If we have that gradient, we need to normalize it because it has to be a vector of length 1. And then also we have to make sure that the orientation is right, because we are talking about the sphere and the vector has to be pointing outward from the sphere. And so we have to check that. All right, but let me first calculate the gradient. So the gradient of f is, of course, the vector 2x, 2y, 2z. All right, and let me start by normalizing this. So the normal vector n now becomes, of course, that gradient divided by the absolute value of that gradient, which is the length. So that's 2x, 2y, 2z, divided by the square root of 4x squared plus 4y squared plus 4z squared. And, well, we have to notice that, of course, we are on a unit sphere. So x squared plus y squared plus z squared is 1. So the square root in the denominator here becomes the square root of 4. That's 2. And so if we divide this entire thing by 2, we get the vector x, y, z. So that's a vector of length 1 if we are on the unit sphere. That's good. Furthermore, this is also a vector in the correct direction. Remember, for a closed surface, our normal vectors have to point outward, and this is definitely pointing outward. So that's good. Right? It's pointing away from the origin, and therefore it's also pointing away from the surface outward from the sphere. So that's answering our question, and we could move on to part C, but I want to quickly mention some other ways which also work, but maybe a little bit harder to, or not harder, but will take more time to complete. So alternatives. Well, it's actually one basic alternative, and then we can work it out in different ways. Of course, what we can also do is we can parameterize that sphere. So we can take, for example, the spherical coordinates and parameterize the sphere as this. You know, cosine theta, sine phi, sine theta, let me get some more space, sine theta, sine phi, and then cosine phi. And then just notice that we can get a normal vector if we take the cross product of the partial derivatives of this vector r with respect to phi and theta. Right, and that would give us a normal vector. It's a lot more work to calculate the thing because, you know, it's a cross product involving terms of cosines and sines, and many of those terms will eventually cancel out or, you know, simplify. And then, so that's already a lot of work, and it's easy to go wrong with minus and plus signs. And then still, you also still need to check the orientation and the magnitude of the vector because we're still looking for a normal vector. So that's one way we can solve that. On the other hand, we can use an alternative parameterizations also. So one way many of you would maybe like to do it is by parameterizing the surface as a function of x and y. Well, that's a little bit tricky because x and y are not good parameters for the entire sphere, right? You can use x and y to parameterize the upper half of the sphere or the lower half of the sphere, but not both at the same time. Well, you can still use this parameterization, but then you would have to show that you get the same vector x, y, z on the upper half and the lower half. So it's basically the amount of work times 2 almost. So, well, okay. So that's another alternative that you may use. It will give you a correct answer, but also it's a lot of work. Good. So that completes part B of this question. Then we have to go to part C, and now we have to prove that this one formula is true. So let us go there. Let me first write up that formula. So this is question number C. The triple integral over B of the partial derivative of f with respect to x integrated over the volume. And this thing is equal to the double integral over the surface of some function g of x, y, and z. And we need to figure out what that function can be. All right, so this is a triple integral that's equated with a double integral. Now that really reminds us of Gauss's theorem. And so let me write up Gauss's theorem. Gauss's theorem states that a triple integral over region B of the divergence of a vector field is equal to the double integral over the boundary, which in this case is S, of the vector field itself. So like this. So let's use what we know about the vector field F to rewrite Gauss's theorem there. So the triple integral that we have here becomes V dot nabla F, because that's what that divergence of the vector field F is. And then on the right hand side we get the double integral over the surface of F V integrated over that surface like this. All right, and well, of course, what we want from this part, we want this to be equal to the partial derivative of f with respect to x, and we can achieve that by choosing a vector v that's equal to the vector 1, 0, 0. So let's choose the vector v 1, 0, 0 and see if we can arrive at a final integral equation. So the triple integral over region B then becomes, well, the first component times the gradient will give me the partial derivative of f with respect to x. That's exactly how we wanted it. And then on the right hand side we get the integral of f times 1, 0, 0. Well, and then the oriented surface element, of course, has a normal, well, I can rewrite that as the unit normal vector n times ds, right? So this thing here is the normal vector. As we've learned in class, it's the normal vector times the area ds. And so we also know, of course, that this is equal to x, y, z. So if I work out the dot product on the right-hand side, what we get is the double integral of f, which of course depends on x, y, and z, times, well, 1, 0, 0 times x, y, z. That is simply x, right? Well, that's actually our final theorem. So we see that this triple integral is equal to this double integral, and it gives us also an expression for the function g, because g is now simply x times f of x, y, and z. That concludes question 9. That brings us to the final question of this practice exam, in which we have to use Stokes' theorem to simplify and compute that double integral. And as you can see, the given vector field is extremely complicated. So, of course, the idea here is to, first and foremost, simplify this integral. So let me start by writing down Stokes' theorem first, and then also try to draw or just give some visualization of that surface S, and maybe we can come up with some clever idea. So Stokes' theorem tells us that the double integral over a surface S of the curl of a vector field F is equal to the single integral over the boundary of the region. And then we integrate F over that thing. All right, let me also sketch the surface. So we have the z-axis, the x-axis, and the y-axis going like this. And the surface is this parabolic surface, the paraboloid, and it looks like this. So the equation is z is equal to 2x squared plus 2y squared minus 8. And it's the part of this parabolic surface below the xy plane, so it intersects, turns out it intersects this surface at this circle and then goes down like this, right? And the surface is also oriented, and the vectors, the normal vectors, are pointing in the positive z direction, so they're sort of the surface is oriented like this. All right, let's also think a little bit about the boundary. So this is, by the way, this is the surface S. It's defined by this. How about delta S? Well, I said it's a circle in the xy plane, but let's check that. If z is equal to 0, we can see that x squared plus y squared is equal to 4. So that's indeed a circle, and it's a circle of radius 4. And let's also look at the orientation of that circle. Well, we have learned that we have learned with the right-hand rule that in this case the orientation is, if we view it from above, it's counterclockwise. So it's like that. Okay, now we're supposed to apply Stokes' theorem, so we have to, I think it's a fair start to think about calculating that surface on the boundary. And the good thing about it is that the boundary is located in the plane where z is equal to 0. By the way, let me add that to this description. Z is equal to 0. And, you know, if z is equal to 0, that will at least perhaps simplify our vector field quite a bit. So let me evaluate the vector field at z is equal to 0. Well, what is it? It is going to be y squared minus e to the power x to the power cosine of x. Oops, that's not so easy. Comma x cubed minus y sine and then cosine of y. That's also not very simple. And then the z component is going to be just 1. Yeah, well, integrating this thing is too complicated for me. Don't know how about you, but this is too complicated. So we need to do something else. Now we can try to use Stokes' theorem again to make life still a little bit easier. And so the idea is that, you know, we started with the surface S, calculate the curl. We need to calculate the curl over that surface. You know, Stokes' theorem tells us it's equal to the integral over the boundary of S. But then, you know, we can simply go back to a double integral over a surface that allows us to simplify our vector field even more. So let me call that alternative surface S1, and let's see if we can come up with something that well, that makes sense. So if I look at the picture of that surface here, of course we are looking at the boundary in the xy plane, but of course that boundary is also the boundary of a region in the xy plane here, which is flat, which has z is equal to 0 everywhere, and which has a very simple normal vector, which is just the vector k. right? Remember, k is 0, 0, 1. It's the unit vector in the z direction. So maybe it's a good idea to use that surface to calculate that integral. And but before we go there, we still need to calculate the curl of f, all right? So that curl is still something we need to calculate, and hopefully that becomes somewhat easier if we take the curl. All right, so let me give you the curl here. Of course, you can calculate it term by term, and you know, it's a lot of derivatives that you need to evaluate, and it's easy to make mistakes, but here's the correct answer. It's minus xz times e to the power minus xyz minus x cubed y e to the power yz. That's only the x component. Not so easy still, but okay. Minus xy squared sine x times z plus yz e to the power minus xyz. That's the y component, also not so easy. And then the z component is 3x squared e to the power yz minus 2y cosine xz. That's a very complicated vector, that curl, but okay, we have a chance. If that simplifies for z is equal to 0, we might have something to work with. So let's check. When z is equal to 0, let's just cross out all the terms that are equal to 0. So of course this term here has z in it, it will be 0. Of course the term here, the e to the power yz, is going to be only 1. Sine of x times z will be sine of 0, and that's going to be 0. Yz is going to be 0, so that's good. E to the power yz is going to be 1, so that one we can forget about it. And also cosine of xz, that will be cosine of x, right? No, z is equal to 0, it's cosine of 0, and that's 1, so that we can cross out. So it seems that our flat plane in the xy plane is going to simplify the curl quite significantly. So let's see what we get in the end. It's going to be minus x cubed y, comma 0, comma 3x squared minus 2y. Well, that seems decent. All right, so let's try to calculate that double integral over S1, our new surface of the curl of f. Okay, so what is it going to be? Well, it's going to be the double integral over the surface. And then the curl is this vector, minus x cubed y, comma 0, comma 3x squared minus 2y. And then the oriented surface element is simply going to be the normal vector, which is the unit vector in the z direction, upward, as we wanted it to be because it's oriented upward, and ds. All right, so the k vector is 0, 0, 1, and then that entire thing has to be calculated over this surface. Good. Well, that is going to simplify significantly. So it's the integral of only the z component, which is 3x squared minus 2y over the surface ds. Well, we're given nothing for free in this exercise, huh? So it's really not that we still need to do some work here. But if I look at our surface from above, so let's zoom into the xy plane, we have this, oops, let me get the right color here. We have this region, which is a circular disk of radius 2. And if I look at that integrand, I see that minus 2y seems to be an odd function if we integrate it over the entire disk. So that is going to give us a 0, because for negative y, the points where y is negative and the points where y is positive in this disk, they are going to contribute opposite signs, and so that's going to vanish. So we can ignore the minus 2y term, so that we have to calculate the integral of 3x squared over the surface. Now that seems to be doable over this circle of radius 2. It makes a lot of sense to use polar coordinates for this integration. So let me then just write that up. So it's going to be 3x squared is 3r squared cosine squared theta times r dr d theta. And r is going to be from 0 to 2 because that's the radius of our disk. and then theta is going to be from 0 to 2 pi. Now that's an integral that we can really solve. So first of all, we can separate out the theta part and the r part. So it's going to be the integral from 0 to 2 pi of cosine squared theta d theta times the integral from 0 to 2 3r cubed dr. And of course we can separate it because our integrand here is just a product of functions of r and a function that only depends on theta. So we can do it like that. Well, the first integral over theta is one I think everybody should know, that this is equal to pi. And don't think too much about it. I can quickly give you a reason, but you really have to memorize this stuff. So cosine squared looks like this, where this is 2 pi, and this is 0, and this is 1. And if I calculate the area of this rectangle, the area is going to be 2 pi. And it turns out that the integral that we're calculating is exactly half of that area. So that is going to give us pi, okay? Just memorize that. Same for sine squared. Okay, and then the other integral is 3r cubed. So this is going to be 3/4 r to the 4th between 2 and 0. And you can work out that this is 16 divided by 4 is 4. So it's going to be 12. And the answer is 12 times pi. There we go. Relatively simple answer for this enormously complicated vector field. And that concludes this practice exam.